Hello everybody. Today we'll be reviewing some Renogy products. I'm building my own DIY solar generator for when the power goes out to keep my essentials running. Mainly my refrigerator, maybe or a deep chest freezer if you have one of those, my router, my modem, maybe be able to charge up a laptop or two, and an Instant Pot so I can cook some stuff with, and then of course my cell phone, but my cell phone uses next to no energy, so no big deal with that one. This is by no means meant to power my entire home. This is really just a small scale setup to power the essentials, kind of as I would with a regular gas generator. But the problem with the gas generator, of course, is that you need fuel to run it. And I don't know about your area of the country, but near where I am, they typically don't have power when the power is out. So guess what? The gas stations can't pump out the gas and you're basically screwed, right? So that's why with this, I can actually just, put this outside, charge it up for about 5 or 6 hours. It'll be charged up for a couple of days, and hopefully by then the power should be back on. And if not, then, just put it out there for a couple more hours. A couple days later, let it charge up, and, you'll be kind of going through the cycle over and over again. This is perfect for those of you who live in like in hurricane-prone areas. Maybe if you have bad winter storms. The poor people in Texas last year had an issue with the power being out for like a week. I don't know if necessarily we'll be able to help them in that kind of scenario. 100%, it's something. Now, the most important thing to do before you start ordering your parts is to make sure you have a good understanding of what you're trying to power and how much energy they will draw. You'll have to do some research ahead of time on this and come up with a realistic and pessimistic scenario of how much energy these items will need to use cumulatively. In my case, my main use case is to power a full refrigerator with a freezer and a few other peripherals. How can we get this information accurately to determine how many watt hours it'll draw over the course of a day? Well, there's two ways we can do this. One is to open up the fridge and see what the max amps are that it'll draw. You can usually tell this by opening up the door and looking on the inside, as I'm showing in my picture. In my case, it's 6.5 amps at 120 volts, so that's roughly 780 watts max. Since this device has a compressor, there's going to be a surge wattage for a few seconds as it clicks on. This is typically 150% of the typical running wattage. This means that I can expect to see a temporary spike of 1170 watts in my case, and I need to be sure that my battery and inverter can accommodate this. Now, this is the absolute worst case scenario power usage wise that the fridge is rated to operate at, and is likely inclusive of any automatic defrost, ice maker, and any other special features that it has. In reality, it'll probably operate at a much lower rate the majority of the time. We do need to use this as a worst case scenario for planning purposes though, since it's important that the system is able to accommodate this. Otherwise, you could grossly undercalculate your system and run into some serious problems. It's always better to overcalculate than to undercalculate. It's important to note that a refrigerator typically doesn't run constantly, as it turns on and off as cooling is needed. You can always figure out the daily usage amount by looking at the energy guide sticker for your appliance. I found mine online because I threw my original one away, and I was able to do a rough reverse calculation for daily kilowatt usage, which I'll share with you now. If we look at my refrigerator's energy guide, we see that it's estimated to use about 443 kilowatt hours of power per year. To get a daily estimated usage of kilowatt hours per day, we'll need to do some quick math here, and a spreadsheet can make some quick and easy work of this. There are 365 days a year and 24 hours in each day, which means that we have about 8,760 hours in a year. This refrigerator uses 443 kilowatt hours, which is another way of saying 443,000 watts. If we take the 443,000 watts and divide by the 8,760 hours in a year, we get a value roughly of 50.6. Now, this is 50.6 watts in an hour. Since there are 24 hours in a day, we need to multiply 50.6 watts times 24 hours, and we get 1,214 watts as our daily estimated usage, which means that it's really powering itself on for about an hour and 30 minutes every single day. You can always be more precise and get a kilowatt device to capture your real-life usage, as it can vary greatly based on how full your refrigerator is, what temperature you're setting it for, what the ambient temperature is around the fridge, and how good the insulation is on it. Also, a full fridge is most efficient to cool, and will keep the longest while generally using the least amount of energy. Even filling up the freezer with freezable water blocks and pouches will greatly help you maintain temperature and use less energy. I always keep freezable pouches in my freezer in the event of a power outage to help extend the duration of how cold it will stay without the power. Now, deep chest freezers are even more efficient than your regular stand-up freezer and should be considered for grid-down use too. Some will use as little as 300 watts per hour and probably double the round time you'll get out of your power setup in this case. As far as my other peripherals, such as my router, modem, maybe charging a laptop, that kind of thing, they typically are lower wattage draws, and at most, maybe it will consume about 100 watts per item. Most likely a little bit less than that, but we'll say 100 watts at a higher end. If I were to power these three extra things at the same time, this would add about another 300 watts cumulatively at any given time that we need to account for in our battery and inverter sizing. Since I'll probably need up to about 1500 watts of power at any given moment, this means that I should try targeting a little bit higher at 2000 watts to give myself a little extra wiggle room. It's always better to have a little bit more power than you'll need. Every watt counts in a grid down scenario. This is why I went with a 2000 watt inverter and a 200 amp hour battery that will hold 2400 watts of energy. I'm confident based on the usage metrics above that I should be able to get about 2 to 3 full days of continuous usage from about 100% charge to, if I had to, 0% charge. It's important to note that this battery has to be a 200 amp hour discharge rate and not a 100 amp hour discharge rate, as that would effectively limit me to 1200 watts max usage, which is below what I would need to power everything. This gives you some insight into how I chose my battery. Related to the maximum battery output that we can hope to take advantage of, we'll need to make sure that our battery cables and fuses are all properly sized to handle this load. I found a terrific PDF on DIYSolarForum.com, which requires a free sign-up. This PDF helps beginners break down the calculations you'll need to go through in order to properly size your setup. This forum is a terrific free resource for beginners to ask questions and get familiar with solar and electrical concepts from the ground up. Now let's go ahead and take this PDF's formula and put it into an actual Google Doc or Excel spreadsheet or something like that, and actually try to go through this in real life. We're going to compare our calculations against the chart that they have here for the wire size and fuse amp ratings. So this is a good basis to determine the minimum cable size you should get to be safe. And of course, this will also play into the type of fuse that you're going to get to put into the battery as well. So make sure you have the proper amperage limit. In my particular case, the inverter is set to be at least 90% efficient. So we'll use that as our value. My cables are only less than a few feet, and anything longer than that can encounter a voltage drop. Subsequently need to have more power going through the lines to make up for these losses, increasing the amperage and likely increasing the gauge of the wire you'll need to safely run this. So for that purpose, I'm going to use these 3-foot battery cables since that's more than enough for me, and I don't have to worry about any voltage drop. If you're doing something longer than this, then you definitely have to use a calculator online to figure out the proper gauge of wire you'll need, because that's going to start encountering voltage loss and you can have a higher current situation. There are many calculator resources that you can use to try to determine this for your own use case, but for my cables that are 3 feet long, this is sufficient. And as you can see here, I can get away with using a 1.0 cable as long as it's rated to 105 degrees Celsius and is copper based. And the cables I bought are rated to 105 degrees Celsius and are copper based, so I'm in good shape here. And as far as my A&L fuse, mine comes out to about 250 amps because that's going to be the next level up. That's not going to be less than the amperage stated here in the calculations. And so this is the proper amperage that I should use in my situation. Now with these 4 panels connected together, we should in theory get up to 400 watts per hour output out of these on optimal sunny conditions, right? So with my battery here being 200 amp hours at 12 volts, that's going to be roughly 2400 watt hours that this battery can store. So if we can do 400 watts per hour in a 2400 watt hour battery, that's going to be roughly, I guess, about 6 hours, probably more closer to 7 or 8 hours, honestly. I'm sure the sun will go behind the clouds and stuff like that and may drop the output, but you're looking at basically about a 6 to 8 hour charge time from 0 to 100%. Now, you really don't want to run your batteries down to 0% because, in the long term, it could harm it. At least historically, it's been the case with traditional lithium-ion batteries or lead-acid batteries, right? In fact, lead-acid batteries couldn't even be taken down less than 50% because they could possibly damage the battery permanently. But they say that these lithium iron phosphate batteries can be discharged to 0% safely, and it will impact the lifespan of the battery, but apparently the lifespan of the battery is so great to begin with, where it can be done, 2,000 to 4,000 times. Maybe you can only get to 1,000 to 2,000 times if you discharge it constantly to 0%. I mean, even still, you're looking at probably 10 or 15 years at that rate if you're truly doing that all the time. So I wouldn't recommend you go below 20% on this. I would actually maybe be a little more pessimistic and go 40%, right? Because what if it's going to be a cloudy day the rest of the day, or if it's going to rain, you don't know about it, right? If you're going from 40% to 100%, or again, you probably want to charge it 100% either. Maybe you want to charge it about 80 or 90%. So you're looking at maybe like a 4-hour charge time between those two, 20 and 80% roughly levels. Now, depending on how you're setting this up, if you want this to be mobile or stationary, we're going to do a couple different scenarios in this video on how to set the system. One scenario will be connecting the inverter to the battery and just running it off the battery like that and powering devices. Another scenario will be basically doing both. We'll be connecting the battery to the inverter and to the solar charge controller at the same time so that the device can be used while it's charging. And, if you're going to be building this onto a hand truck or somewhere stationary, basically where it's going to be kind of a permanent installation, this is probably the way you want to go. So you don't have to keep installing and reinstalling things over and over again. You can just kind of set it up once and that's basically it. Or if you want to keep this mobile and portable and want to be able to break this down, you can certainly do that too. Let's go ahead and get started. And to do this, we just need basic tools. We definitely need safety glasses because we could be dealing with sparks, which could possibly harm our eyes. A basic wrench here to tighten down the bolts, mainly onto the battery, and a Phillips head screwdriver. Optional are power drills, and obviously if you're going to be mounting this somewhere, you probably want to obviously have the proper screws and bolts. Let's go ahead and crack open the starter kit and see what we got in here. Okay, so we have our battery terminal cables. This is going to go from the charge controller to the actual battery itself, positive or negative. Looks like this is some kind of mounting, yes, this is metal, some kind of mounting hardware if you want to use that. I'm not going to be mounting it to a roof or anything like that, so I'll probably skip on these, but if you wanted to mount it to your roof or your RV or anything like that, you certainly could do that with these mounting brackets and screws. These are the branch connectors. Looks like this is a 2-to-1, so it only connects 2 panels as one. I bought that 4-in-1 branch connector, so we're not going to be using this today. We have these extension cables. These go from the solar panels to the charge controller, both positive and negative, of course. And we have our charge controller itself here. Let's go ahead and get this out. Standard Wanderer, PWM, nothing fancy. You know, again, for basic system we're going to be using maybe once a year at best or something like that, hopefully. The energy doesn't go out that often. You know, this PWM charge controller is just fine. But again, if you want to upgrade to an MPPT charge controller, you could certainly do so. They cost a little bit more money, but they're more efficient. Maybe will last a little bit longer. But for our purpose, this serves the purpose. And the instructions, of course. This is a 30 amp charge controller, so definitely more than adequately sized for our system that we're going to be having here. If I had to venture a guess, I'd probably say this is no more than about 22 or 23 amps with our 4 panels together, so we're still well within the range of tolerance for these. Just to show you what the panels look like out of the box, here we go. We have the dimensions here, roughly about 21.5 inches wide and about 42 inches, maybe about 41.5 inches long. You see here they are stamped Renogy, of course. They're pretty heavy duty. Seems like they're pretty resistant. They actually just shipped in that box over there, which I was kind of surprised. I thought for sure they would come back broken with FedEx or UPS, but no, actually they're pretty resilient. So, you know, I guess obviously these are meant to be outdoors, experience hail and that kind of thing. If you put them on like an RV or whatever outside, they're gonna get beat up out there, right? So they are pretty resilient. And just to show you the back side with the connectors and all that kind of good stuff. So we have here the positive side, clearly marked off here in red. Negative side's over here. And then we have some specs here. And, okay, so this is important information you want to know. Basically for fusing and that kind of deal, or just overall how many amps are coming through this and how many amps your wire coming off this would support. It's all back here for you. So you see here, max power is 100 watts optimally. Short circuit current is 5.21 amps. And we have max series fuse rating 15 amps. And of course the dimensions too. So the way I chose to fuse this, and I actually reached out to Renogy about this because I was a little bit uncertain about some videos that I saw online, but basically they said to take the short circuit current and, you know, depending on how you're doing this, if you're fusing it on each panel like I am, then I can get away with a 10 amp fuse because 5.21 is within the 10 amp fuse limit, and if there's over current situation, I would still be safe. If you're fusing this basically at the main line, so after all 4 branch connectors have been connected for each panel to the main wire going to the solar charge controller, in that case your fuse would have to be a little bit bigger and different, right? So if you're fusing on that end, you would have to basically take the sum of this, so 5.21 times 4, that's going to be probably about 22 amps, I guess, roughly, and you probably have to get a more appropriately sized fuse to hold that in between your charge controller and the branch connectors. So that would probably be, I think it's closer to a 30 amp breaker. You know, that's if you're doing it that way. In my case, I chose to fuse it on each of the positive branch connectors of each of the panels, so I got 4 of those. May not have been the cheapest thing to do, but honestly I thought it was the easiest thing to do because I am kind of a beginner with this and I don't want to take any chances. So, and of course you see we have all kinds of holes, pre-made holes for you for mounting being with the brackets, that kind of thing. You'll see I have here some magic marker on my framing here. That's because I'm going to put some holes in there to do some custom stands of my own using some PVC that I saw another guy use on another YouTube video, which is pretty good. No point in recreating the wheel. He did a very good job with that video. But yeah, so ultimately what's going to happen is my PVC pipes are going to be put together in a stand configuration. I'll drill through them. They'll be mounted through here, and then I can stand these up pretty much any which way I want to. It was pretty cheap. I mean, it was about $40 for the PVC. I know some of these stands, these metal stands that Renogy is selling, I think they're like $30 or $40 a piece or something like that, or maybe a 2-pack or something like that. I'm not sure, but they get kind of pricey. So doing the PVC thing, you know, again, because this isn't a permanent installation, it's more of a grid down scenario kind of thing. No point in spending all that money for something I'm going to use probably a handful of times a year or less, hopefully. Okay, we've got the box open here. Super well constructed box, double corrugated. Hopefully this will be nicely intact. All right, we've got the instructions. Got some little sticker things here for you. What are these? Something in German. Can't quite read that. Well, we'll put that to the side for now. Oh, this is, okay, a couple selling points behind this Bluetooth connection. We'll get to that in a second. Member benefits, community. My warranty card. All right, nice. Yeah, so the cool thing about this battery is that it actually has a BMS that has Bluetooth on it. So you can just kind of, you know, install the Renogy app on your phone and see how you're charging, discharging, you know, what the voltage of the battery is probably, the temperature conditions, all that kind of stuff. So you don't really have to be tethered to it. You know, if you're kind of nearby, you can just kind of check on your phone and just be on your way and do things that I hadn't monitor things closely with the old school indicators and gauges and that kind of thing. Looks like we have some cap covers here, and of course we have some terminal bolts. Let's get this opened up a little bit more here. Okay, seems to be in very good condition. What else we got going on here? Oh, so we have some handles to this. Oh, that's cool. So I have some handles here so we can pick it up from place to place really easily. So this battery is a pretty decent size, and it's got a relatively decent weight to it too. It's about 19 inches wide. I have to estimate that weighs probably around 40 pounds at least, roughly. It's pretty dense. So if you're planning on kind of keeping this portable like me, you definitely want to go out there maybe and get like a hand truck, kind of like the ones that the UPS and FedEx drivers use to deliver packages with, just because, you know, kind of will hurt your back after a while if you have to constantly bring this around. So for those of you trying to stay mobile with this thing, definitely want to consider using that as an option. The handles do work pretty well though, I do have to say they're pretty good. So no issues with that. Now looking at the instructions here, we see a couple of things here. So number one, it's saying here that the battery can be safely discharged to 100% depth of discharge, which is fine. You know, I know with the other old school lead acid batteries, that can definitely damage it, and the discharge was probably like 50% or something like that. So definitely not as low as discharge that you would get out of the old batteries compared to these new batteries. And also this is rated to about 2,000 cycles, probably at the lowest, with the 80% depth of discharge on average. So again, try to target that 20% as a low end, and actually as a high end, definitely try to cap it at about 80% as well, unless you know you're going to be in a situation where you may not be able to generate power, solar power, through a couple of days. Maybe you're expecting some bad weather and you won't be able to generate some energy for a couple of days, so maybe you want to top it off at 100%. You know, again, every so often, probably won't hurt the battery too much. And then you'll notice here that we have some other information. Okay, so they give us this little handy copper gauge sizing chart based on the amount of amps you're trying to push through this. Now I have a 2000 watt inverter, so definitely probably better to overstate what you need as far as gauge sizes are concerned, rather than understate, because if you understate, you can get some serious issues, possibly even fires, because the cables could overheat. Whereas, you know, overstating what you need, there's really no drawbacks to that per se. Yeah, you may be overpaying for some of the wiring, but you definitely stay within the specs of what you need it for. Also important here is that this battery cannot be connected in series. Doing so can cause catastrophic failure. So, you know, I'm doing this just by itself, just with one battery. But for those of you who have larger solar banks, you want to get a whole bunch of these going. You cannot wire these in series. It can only be done in parallel. And I believe it's up to about 7 or 8 in parallel maximum. So a decent amount of capacity in that regard. But if you're trying to do series, yeah, you're not going to be able to use this battery, unfortunately. As far as storage, you know, this is pretty applicable to me because I'm not going to be using it all the time. It's just kind of like an emergency thing. So when I use this, I definitely want to keep it to about 30 to 50% when I disconnect it from the system. And you know, definitely check on this voltage every so often to safely keep the battery in storage. You don't want to go past about 150 degrees. So those of you in that kind of environment would have an issue, but you know, you probably don't want to keep it in a place like a garage, because you know the garage can get super cold depending where you are. So if you're in an area where it's cold in the winter, you get down to 0 degrees. Definitely don't want to keep it in that kind of an area. Also, if you're going, you know, if you're in an area where it has like 150 degrees, don't want to keep in that kind of area either. All right, let's open up the inverter now. What do we have here? Okay, looks like we have the remote switch, so you can actually be about 10 feet away from the inverter if you wanted to mount this and you know, activate it remotely, kind of like that. So you know, this is more for a permanent installation if you have like an RV or something like that, and you know, you don't want to be bothered with going down and flipping the switch every single time. You can actually just plug this in and put this wherever you want to externally, you know, on your wall or counter or whatever it is you put this on your RV or mobile home or whatever it is you're running. So kind of a nice little convenience. They provided this with these cables, which is good. It should be rated to support the maximum wattage of this. Now I did reach out to Renogy support regarding these 4 AWG cables that they included with this 2000 watt inverter. And the customer service seemed to confirm the fact that they would not in fact let you go to the full wattage of this inverter. This is their response on the screen. This is kind of perplexing as to why they would do this, unless there's a translation miscommunication, since I think a lot of their support might be overseas in China, if I'm not mistaken. I have seen some people on some forums mention that because they are twin 4 AWG cables bonded together at the terminal lugs in the end, that they should be able to handle the voltage needed for 2000 watts. But I don't know, I'm still a bit concerned by this, so that's why I decided to spend the extra money on the 1.0 or 1/0 AWG cables that are rated to 105 degrees Celsius and about 285 amps. Just because I know in that case it'll be able to take the full capacity if I had to. So what I wound up doing was buying these 1.0 Windynation cables off Amazon. They're really thick and they're more than appropriately sized for my system here. So, you know, I don't have to worry about any kind of electrical fire or anything like that, right? Because if you do wind up using a thinner gauge cable and you wind up drawing too much amperage through it, it could possibly overheat and cause a fire. So safety first. There's really no drawback in getting, you know, a thicker gauge than what you need. You know, aside from spending more money, of course, it's not going to do anything bad if you have a thicker gauge than what you're going to need, because you know, it's not going to like slow anything down or cause any issues, right? Obviously there's a cost issue, but whatever, you know, I'd rather pay an extra $10 or $15 more than these size cables and be safe and not have to worry about anything. And you know what, who knows in the future, maybe you expand the system and you know, you need to draw more amps through it. Well, guess what, if you have a thicker gauge, you're good to go, you know, possibly, depending on your size, of course, but there might be some element of future-proofing to this. Got some more stickers, warranty cards, some more German writing. All right, we've got the instructions, great. And we've got the inverter. It's a pure sine wave inverter. So probably generate cleaner energy than what you're getting out of the plugs today out of your house. Let's get this out. All right, we got this out. Pretty decent size for this thing. Probably about 1.5 feet long, at least about a foot wide. So definitely some mass to this one. Here's the business end, I guess you could say, of everything. This is where you connect your positive and negative terminals, and here's the exhaust. And of course, we have the parts where you can actually go there and plug things in. So you got 3 AC power ports, and so just 1 USB spot for you, 2.1 amps, so decent amount of power coming out of that. You can actually hook up the remote through here. This I kind of showed to you earlier. And of course, this is the on-off switch. We have some LEDs for the power, ground fault indicator, and looks like some kind of warning light. Something goes wrong, maybe with a short or grounding or something like that. Actually, well, not grounding, but something along those lines. And I think this is for some kind of more permanent connection. I'm not really familiar with this kind of stuff, but yeah, that's something that probably I would not use for my use. Now the terminals to this come with these little plastic covers for safety purposes. You definitely have to remove these before you put the cabling on. Do not attempt to put the cabling on with these on, because you won't be able to do it basically. So yeah, definitely slide these on while you're installing the cables basically. Now these fuses are actually 10 amps each, and you have to be very careful with these. I actually reached out to Renogy just to make sure that I was buying the proper amperage for these, but because each one of my panels is about 5.5 amps a piece, And because I'm running this onto the branch connectors, their recommendation was to use a 10 amp fuse for my particular case. If you're using these 400 watt panels like I have, then you'll probably be the same situation. If you're going to plan on putting the fuses between each cable and a branch connector anyway, you might be able to have a breaker at the end of this this cable here where they all kind of commingle together into one cohesive source, and have a bigger breaker on that. That might be like, you know, maybe about 30 amps or something like that. You have to do your research on that one. That kind of added more complexity to the mix. I just wanted to keep it super simple, right? So whatever. If I have to buy 4 of these, then so be it. I just, you know, slap them on between here and the panel, and I'm good to go and I'm safe. So, you know, it's up to you how you want to design this. I kind of did mine for ease of use because I am a novice and not a professional, right? So I figured let's just be safe and spend a couple extra dollars on whatever. Now you'll see I have 2 different types of fuses here. This is an A and L fuse. There are actually 2 in here. No, you do not run both at the same time. You would take this out, obviously, and put one at a time and put your lugs in and run it like that. And then here is a bolt-on fuse, which a lot of people are using online too, which is fine. The bolt-on fuse, you know, originally I was going to use this to bolt on to the positive end of the battery and the lug of the wire. But then I was doing some research on these, and a couple of things I didn't like about this in the end. Number one, these bolt-on fuses, they're actually supposed to be put into a fuse holder. So they're not actually supposed to be bolted onto the battery itself, hanging out there with a cable like that attached to any other end of it. You know, it's not really a weight-bearing structure, so you can possibly, you know, I guess damage the fuse while doing that. If it's putting too much pressure on it, it could possibly, you know, break apart the fuse and cause the electricity to stop. The other issue is that, you know, if you're running it with the bolt-on fuse just like that without the holder, these fuses kind of pop, and the plastic here, wherever this material is made out of, will actually split apart. So not that there's going to be an explosion per se, but, you know, the pieces could shrapnel apart, and if you have like a pet or a little kid or something like that, you don't want them to possibly ingest it. You know, it's kind of another thing I didn't want to deal with either, possibly happening. And then third, the other issue is that these do give off a little bit of a spark when they do burst, and I may use this in an area near where I have some natural gas. So if I wanted to run, for example, my heating for my home and power the, you know, the motor for that for my baseboard, a possible issue with that could be, you know, this thing could possibly pop and spark, and there could be some natural gas nearby and possibly cause an explosion. I know it's probably not really likely, but I like to be paranoid and safe with this kind of stuff. So instead, I want to buy one of these A and L fuse sets from Windynation. The A and L fuses are a little bit different. When they break, you can kind of see here, there's a little window in there. There's something that will basically pop out. It'll just show in the window it's being broken. And there's also a little spark as a result of this. So that's why I went with these instead. I do think they might be a little bit more durable too than the mega fuses too. I think they have a bit of a higher threshold before they pop, which may or may not be a good thing. But I mean, I know on more higher end systems, they use these A&L fuses because they have a higher amp rating than the mega fuses can go to. So future expandability, if you want to do that, you know, you can kind of do that too. You already have the holder for it, right? So you just need to buy the higher capacity fuses for that kind of thing if you're going to upgrade this in the future. And it even has a spot here on the bottom too where you can mount this. So I'm going to mount this onto a piece of wood board, and we're going to get this all nice and done right. And of course, I have an extension cable. This is about a 9-inch cable, also 1.0. One thing to know about these extension cables is that the length definitely goes from the lug terminal to lug terminal. So if you're expecting this to be 9 inches wire-wise, and then in the lug terminals, you're in for a rude awakening. You will lose about 2 inches of length if that's what you're expecting, right? So this is actually 9 inches end to end, but you know, when you actually count the actual wire itself, it's probably only about 7 inches. So just make sure you size accordingly when you do buy this. In my case, it's going to be, you know, not that big of a deal for me. That's actually why I bought the shortest one that they have, because hey, I don't need anything longer than this. So I'll probably put this end here on the inverter, this end here on the terminal lug here, and then the other end here will go to the battery, and we'll be straight. So this here is a resistor. It's a 50 watt, 25 ohm resistor. The purpose of this is that we're going to use this on the wire going from the inverter to the battery. Basically, before we connect the wire of the inverter to the battery, we want to make sure there's no spark between it, or try to minimize the chance of a spark. Basically, what happens is it could possibly damage the components of the inverter over time. So this helps to charge up a little bit slower so that it's not going to just kind of bum rush the current into the inverter and cause a spark and possibly damage the capacitors too. So basically, we'll put this between the inverter lug and the battery terminal for a couple of seconds. It'll build up a charge slowly between the two, from the battery into the inverter, and then afterwards it should be safe to connect the wire of the inverter to the battery afterwards without any spark as a result of using the resistor beforehand. And we're ready to not use the inverter anymore. What we can do is just use this resistor again to discharge the capacitors slowly again, and this helps regulate the flow of electricity. So that's all resistors do. They just kind of regulate the flow of electricity just to kind of resist and slow them down a little bit. It kind of helps to avoid any kind of bum rush of unrushed current or anything like that. So just tries to keep the electronics safe and avoid any kind of sparks if possible. And because this is a 12-volt system, I'm not really sure how much there's going to be to begin with. If it's definitely a higher voltage system, definitely more of a chance of a spark, that's for sure. So it might be a little bit less critical to do this on a 12-volt system, but, you know, let's just be safe. We paid a lot of money for this equipment, and I think this was like, you know, $5 or $10 in a twin pack on Amazon. So, I mean, we're talking about pennies on the dollar here in comparison. So let's just be safe here and protect our equipment. So here's the runtime I'm going to use to make my battery holder and inverter stand, so that when I deploy this, I can tie up everything neatly, and you know, it's not laying on the floor or anything like that. It's going to be all nice and organized and look good. And then ultimately I'll attach it to a hand truck. So over here I'm going to be using 8 of these 2x6s that have been cut to 9 inches in length. These are going to form the corners, which are going to be mounted to the top of this platform here. This platform is made of 2x8s. I have 2 of them, and they're cut down to 25 inches. On the sides, I'll be making 4 of these 2x6s that are cut to 14 inch in length. And then for the front, I'm going to have 4 of these 2x6s that have been cut down to 29 inches. And over here we have my Craig jig and my screws. For these 2x8s, I have to look them up to see which is the most appropriate length of screw to use. I might get away with 1.25 inches. I might wind up using the 2.5 inches. I have to see what the guide says, but ultimately I'm going to use pocket screws to join this together and use glue to make it even more secure. And actually, for all these pieces here, every time I screw them in, I'm going to also use some glue as well to make it as solid as possible. I'll put a cut list too below in the video for all the stuff that you'll need to do this. And to secure the wood that I'm not going to be using pocket screws on, I'm going to be using these exterior screws, probably either 3.5 inch or 3 inches in length. Definitely want to make sure we get this to be really nicely screwed in between the 2 pieces of wood. I want to make sure it's nice and long so that it goes in there nice and deep and is nice and structurally secure. Alright, so pocket screws are in. Everything's glued up, as you can see too. I'm going to let this set overnight. And definitely go with the 2.5 inch screws for the Craig jig. 1.5 or 1.25 is definitely too small. 2.5 inches was perfect. Got some nice deep coverage in here. Join these together nicely. And we'll let this set up overnight before we start assembling the rest of this. In the meantime, I can start assembling these corners. Just using my construction screws. Get these ready to go. And then tomorrow I can mount these to this platform underneath. And this will kind of give a side structure support to the box so that when we put the side pieces in, everything gets in nice and solid and has as many point of contacts as possible. Okay, so now that my bottom platform has been allowed to dry overnight with the wood glue, and also the side corner pieces have been glued and drilled together too, I'm ready to basically mount these corner pieces to the bottom platform underneath with screws. I just put the battery here before I made everything permanent, of course, to make sure everything fits nicely, that it's not going to be too tight or anything like that. And I have just enough clearance, just, you know, not too big, but enough to move it around. I don't want this thing to be totally form-fitting or anything like that. Just want it to be reasonably snug and has some room to move around with and that kind of stuff. So let's just go ahead. We're going to basically take these pieces. We're going to drill up from underneath under the platform, glue these down as well, make everything super tight and solid so that it supports this whole structure if it gets moved around or whatever. I've also gone ahead and I've removed these covers, which we'll put on after we put the cabling on, and I've removed these 2 bolts that are underneath these terminal screws. As you can see here, we have the screw, it looks like a lock nut washer, and possibly a washer underneath that too, I'm not sure, or maybe it's just a regular washer, I'm not sure. These bolts are actually the same size as the battery terminal bolts, so you can use the same wrench over for this purpose too. Here's the bolt removed, and we have a couple of different ones on here. We have a lock nut washer and then a regular washer. And the order will stay the same when we put this back on. So I'm going ahead, let me put this back on. So I'm going to go ahead and put my negative terminal on the negative side and put the bolt on. Let's try to keep this nice and straight. Okay, as you're doing that, let's go ahead and put the bottom bolt on and make sure it's going to stay nice and tight with it. Screwdriver comes in handy with this part. Definitely want to get a thicker screwdriver. Mine's a little bit on the thin side, but it's okay. It'll work. Let's make sure we're threading that bolt on the bottom as we do this. It can be a little bit tricky. Let's put a wrench on here. Okay. Let's go ahead and try to tighten this down a little bit more. Okay, that's nice and snug. Okay, now let's go ahead and slide in this plastic cap here for safety purposes. We don't want anything making contact with the terminals and possibly shorting anything out. So let's go ahead and slide this on like this. So I have the first pieces on. Perfect. Now let's go ahead and put our positive side on. Now in this case, because I have my A and L fuse that I'll be using here, I'm actually going to keep this with a short wire first. So basically I'll go like this, and then I'll have the A and L fuse on this side, and I'll use my longer wire to actually connect the battery. So that's just me. If you have a longer wire, that's fine too. This is just what I'm doing on my own. Next, we're going to connect to our A and L fuse. We're going to open this up. We're going to take out one of the fuses, and we're going to put in only one fuse only, and then connect our two positive wires to each end of this before we attach this to the battery. I'll put a graphic on the video to show you what the proper order is, but basically it goes cable lug on the very bottom, then a flat washer, then the A and L fuse, then another flat washer above the A and L fuse, then the bolt nut, and that's pretty much it. I'll put a graphic on the video just so you can see for yourself. I know it could be kind of confusing, and I don't want people to make any mistakes. Okay, so I took apart the A and L fuse case and holding. Pretty simple. Basically just squeeze this, squeeze that, and it releases like that. So, piece of cake. What we're going to do is we're going to take both of our positive wire leads, we're going to put them on the bottom, like so. Yes, it's very important you do this at this stage in the game. You don't want to start doing it on one side only, and then, you know, not going to be able to get the fuse out properly, so, or fuse in properly, rather. So let's just go ahead, just try to put this down like this. A little tough because these wires want to keep moving up because they're pretty thick. So let's put our washer on. We'll do one side at a time here. Okay, another washer. Let's go ahead and put the A and L fuse in, like so. Just be careful to put too much pressure on the center so you don't break the fuse by accident. I'm going to put another washer on top of that, on both sides. Okay, next we're going to put our lock nut washer on top, and finally the bolt. And just hand tighten it down nice. You don't have to go crazy with it. It just doesn't need to move around. Okay, that's good. All right, let's go ahead and get our lock nut washer on this side. And finally the bolt. And again, try to keep these nice and straight. And hand tighten this down nice and snug. Perfect. Before you close this up and put the cap back on, definitely use a wrench to tighten this down a little bit more. You know, you can get a pretty good snug fit by your hand, but it's not going to be 100%. So don't go crazy with it. Just get it nice and tight, you know, not too tight where it's going to, like, you know, break anything, of course, but just make sure it's nice and snug down. So use a wrench like this or this, either way. This is how it should look afterwards. See, there's no gaps in between any of the washers or lock nut washers or anything like that. And finally, let's put the safety housing on top here. Okay, takes a little bit of finessing, but you can get in there. And in my case, got a decent amount of clearance here for the entry. I'll probably tape over this too. Always read the manual for your inverter before you do anything, especially when it comes to mounting rules. If you look over here, it says the inverter should never be mounted vertically on a vertical surface. Otherwise, present a hazard for the fan opening, and it's crucial for cooling the inverter. So, you know, some people mount this thing, you know, vertically like this on a vertical surface, which I've seen quite a lot of actually on YouTube, but for this inverter, it actually says not to do that. So I'm going to be mounting this horizontally. This is why you're going to see in a little bit why I mounted, or why I developed my stand to have a horizontal mount as opposed to a vertical mount to be compliant with all the ventilation requirements for this inverter to keep it safe. I'm going ahead and mounted my solar charge controller above my inverter just so I can try to more effectively manage my cables. Next, we need to run the wiring from the charge controller to the battery using these cables here that came with my kit. You'll see here in the end that you have this little rubber piece on there, but it slides off pretty easy. As you can see what I did with this other one over here. It just kind of slides right off, nothing to it. Let's go ahead and get a screwdriver because we have to undo these screws just a little bit to get this in here, and then clamp it down, and then repeat this for each and every one. In this case, it doesn't make a difference which wire you use for positive or negative. They both work the same, so don't worry about it in this case. When it comes to the battery tray cable, it doesn't make a difference. Let's just unscrew this here. So we go for a battery over here. And let's insert our first wire underneath here. And let's clamp it down with a screw. Now you want to pull on this just a little bit, make sure that it's in there tight. Otherwise, if it falls out, this is obviously going to be a hazard afterwards. So make sure it's nice and tight in there. You don't want to screw down too much, just want it nice and snug. See, in my case, it fell out. I wound up having to use a smaller screwdriver because the original one I was using was a little bit too big for this hole here. I couldn't quite get the screwdriver all the way in. But now if I pull it, it's nice and tight and solid. So let's go ahead and do the next one. Again, let's put this up here all the way. And screw this in. Okay, that's nice and tight. That's nice and tight. We're good to go with this. Actually, let's tighten down this a little bit more just to be safe. Okay, that's not going anywhere. Next, let's go ahead and connect our solar panels if we want to. So this is kind of the fork in the road. So if you're just using this just as a battery station by itself, the next step would be to attach the battery. If we want to charge the battery, we would have to connect our solar panels to the charge controller next. I'll show you that in a little bit as well. For now, we'll just go ahead and connect our battery to our inverter and just see if we can get something powered up. Just make sure the system's working. And then if it does, let's go ahead and try powering our fridge with it. Now, before I connect this to the rest of my station over here, now that we have the inverter and the charge controller set up, I want to go ahead and try testing out the voltage in this to see if it's fully charged or needs to be charged up by the solar panels, or, you know, what kind of status it's in. It's been sitting around for a while, so it might be getting a little bit low at this point. So let's go ahead and check out the voltage using our multimeter. We set this to 20 volts DC, and we're going to test out the terminals, red for positive, black for negative. Okay, we're about 13.19. You don't want to keep these batteries 100% charged. That's not good either. Probably want to shoot for around between 50 to 80%, I would say, if you're storing it for a longer period of time. I'm just going to top this up a little bit just to show the video of how to charge up the device. But we're well within tolerance of safety range of charging this up a bit more. This is an example of what happens if your multimeter doesn't have fully charged batteries. You'll start getting weird results like 16.5 volts or higher. The battery is not even capable of holding that kind of voltage, so you know something's wrong. Once I changed the battery in my multimeter, the voltage of the solar battery was 12.5 volts and badly needed to be charged up. Here's an excellent battery voltage chart that Renogy published that shows you the battery voltage and the corresponding estimated percentage of charge in them at each level, including levels that are possibly dangerous to the health of the battery. As you can see, you really don't want to go below the 12.9 volts with the lithium iron phosphate batteries if you can help it, just because at that point it's kind of getting into the quote-unquote danger zone. But again, as long as you make a habit of it, I think it's okay to dip down into there every once in a while. But I definitely would not store the battery at anything lower than that because you could be risking longer-term lifespan issues by doing that repeatedly. Very important, before you do anything with connecting your battery to your inverter, always make sure that the inverter is set to off. Otherwise, this could possibly cause a minor shock. Okay, so to do a quick load test on this to see if this works, I'm going to drop in my battery into my little stand here just for the time being. This is not going to be the permanent location of this, just for now. We're going to connect our inverter first to the terminal, and then we're going to connect our charge controller, solar charge controller, on top of the terminal for the inverter, and we're going to fire this up and see how this goes. Now, as I mentioned earlier in my video, I bought these resistors. These are 50 watt, 25 ohm resistors. Hope it comes through on there. If not, I'll put a link in the description, of course, too. We want to use this to kind of pre-charge the inverter capacitor so that we don't accidentally spark anything or possibly damage the inverter too with the sudden rush of current. So we're going to basically use this as a link between the battery and the inverter before we do anything. Also, we also want to have our inverter wired up first. So we have our cables already on there. You don't want to put the cables on afterwards. You don't want to connect them to the battery first and then to the inverter because that could also be bad too. So we have our inverter already wired up, ready to go. Let's go ahead and take our positive cable and let's put it onto the battery. Okay, I'm just going to hand tighten this for now. Next, let's carefully grab our negative wire. We're going to take our resistor, we're going to touch the tip of the inverter lug, and then we're going to touch it against the negative of the battery terminal. So let's just put this here to the side for now. Let's get our negative terminal undone. Okay. All right, so let's go ahead and touch this resistor against the negative wire terminal, and we'll connect it against the battery as well. Just going to keep it here for a couple of seconds. We want it to pre-charge. And there shouldn't be a spark after we connect the negative terminal to the battery. Otherwise, there will be a spark. And, you know, it's not dangerous or anything like that. This could, well, literally shock you a little bit. Okay, there's no spark. Okay, so for a quick load test, what I've done is I've got this old microwave that I pulled out of the garage. It's like 20 years old. It's pretty decent as far as wattage is concerned. According to the back of this, it is actually 1.2 kilowatts, so 1200 watts of energy. We have a 2001 inverter, so no issue. I wouldn't run this probably while I'm running the refrigerator because that could be an issue, obviously. That could possibly cause an overcurrent situation. I mean, it'd be kind of borderline. It would have to be running at max wattage for the fridge and the microwave at the same time, so you could probably get away with it, but I'd probably just be conservative and run one at a time, just in case to alternate it. So the inverter is obviously off. Let's go ahead and try flipping it on. Here's the BMS reading for the battery as I turn on the inverter. You'll see it draws about 1.5 amps at ambience with nothing running on it, and just the inverter by itself. While this may not seem like a lot, if you keep this on for like 24 hours or more, it can really start to eat into your battery life. Okay. Well, we're beeping and we're green, which is good. And the microwave is on. Let's go ahead and just try putting it for 30 seconds. Nothing's in there. Just running it just like this to see what happens. The inverter is super quiet, doesn't seem like it's doing much work at this point, so definitely not breaking a sweat running this microwave. In fact, this microwave actually uses more energy than my fridge does, aside from the surge current, of course. The surge wattage is maybe around 1300 watts, I think, for my fridge, but otherwise, the operating wattage for my fridge is only about 700 watts roughly, so if I can run this, it's going to run the fridge like a champ. Yeah, nothing. Totally quiet right now. Nothing bad going on. I think we're ready to charge this up a little bit or run the fridge. Alright, so I got my 4 panels out. As you can see, I've added those little stand brackets I made. I found this from another YouTube video that was very helpful. Really good, cheap solution using some PVC pipe here. Does the job. And I have my, obviously, positive and negative wire to connect back to the solar charge controller. I have my fuses, 4 fuses for 4 panels. And I have my 4-in-1 branch connector. So, obviously, I have the panels facing down because I don't want them energized right now. And, you know, when you put them down, obviously be careful where you're putting them. Make sure you don't have any rocks or any kind of hard things that could possibly scratch or break the glass. If you're like me, you got a dog, just make sure there's no poop either. That's very important. You don't want any poop on your solar panels. That would be pretty gross. So now I'm just going to go ahead and I'm going to connect my fuses first. And I'm going to connect my branch controller. And I'm going to connect the branch controller back to these 2 wires to the solar charge controller. And then we can start charging this up again. You'll notice that I'm plugging in the solar panel fuses really easily into the positive leads of the solar panels themselves. We'll start to experience a serious issue though when we start to plug in the fuses into the 4-to-1 branch connector that I purchased separately. For some reason, the majority of these fuses don't fit, which we'll go into a little more detail in a moment. For some reason, the majority of these Renogy inline fuses didn't quite fit into the 4-in-1 branch connector that I purchased from them. As you can see in the video, I was having some difficulties and I had to stop and basically just not use them in this case to get my panels connected to my charge controller. Out of the 4 that I purchased, maybe only 1 fit perfectly. The others were incredibly tight and I couldn't safely get them in. In fact, I had tried to force one in a little bit and I wound up getting stuck and I barely was able to get it out of the branch connector that I had purchased. To Renogy's credit, I did file a complaint with them and they did send me 3 replacements. However, these replacements also didn't quite fit into this branch connector well either. Again, maybe 1 or 2 actually fit in and the other ones were just a bit tight and I couldn't get them in still. I did try the inline fuses with a few of the regular single solar cables I have laying around, and they all work perfectly with these fuses. So I had to venture a guess that something with these 4-in-1 branch connectors is slightly off in a manufacturing perspective. Maybe they're just a millimeter too tight or too short or something like that. Because the inline fuses should just kind of slide in as you would with any other solar cable. And unfortunately, these are just way too tight. I mean, they should be snug and everything, but this is basically almost impossible to get in and even more impossible to get out. You definitely don't want to force it. I made that mistake. I really pushed one into the connector and I was pretty close to getting it in, but it didn't quite get it in. And then it was almost impossible to get out. I really thought I was going to have to cut it out with like a Dremel, but thankfully I was able to wiggle it out with a screwdriver between the 2 MC4 connectors. So what I'll probably wind up doing is just make my own solar cables, maybe make them about a foot length, just between the 4-in-1 connector and the fuses themselves, so everything works properly and is fused properly. It's possible that another manufacturer's 4-in-1 branch connector, like Bouge RV, I see they make one as well. It's possible that theirs might work a little better than the Renogy one. Again, I'm not sure why this is the case, but it could be just a batch of 4-in-1 branch connectors I had purchased, and Renogy just maybe had a slight manufacturing issue with them. I don't really know. But this is my experience with this, and this is why I couldn't use the inline fuses in this case. So off screen, I connected my solar charge controller to my battery and ultimately the panels to the solar charge controller too. This was filmed on December 17th, which is probably one of the worst days of the year to charge up since it's one of the shortest days of the year. And of course, the sun is not very high in the horizon, it's actually very low in the horizon. So not much charging time is there for you compared to maybe in the middle of the summertime, like in July, when the days are longer and the sun is higher up at an angle and gives you a little bit more extra charge capabilities. Even still, the panel was still charging pretty well for the time of day and time of year that it was, so ultimately it was not terrible, but you could definitely get a lot more if it was the summertime. So this is a very important piece. Before you hook up the wires to the solar charge controller from the solar panel to the charge controller itself, make sure the panels are either facing down or covered by a thick blanket or something along those lines that'll block out the sunlight and energizing the solar panels. You do not want the solar panels to be energized by the sunlight when you connect them, only because it could be a little bit of a shock hazard, and you possibly could even short out the charge controller in some circumstances. But it's just better to be safe. And then you can go ahead and connect the negative and positive lines to the solar charge controller. After your panels are uncovered and are facing the sunlight, your solar charge controller's PV light should start blinking, just like in my video. When this happens, you know that you're getting power to the charge controller and ultimately, hopefully, into the battery if everything's connected properly. This means that your panels are generating power and the charge controller is regulating them and putting energy back into the battery if everything's done properly. After you've connected the solar charge controller to your battery, you should notice that it will start to blink. It'll likely blink a green color at first, which is for the old school lead acid batteries, and you'll need to change this to be for the lithium ion battery instead. And yes, lithium iron phosphate batteries do count as lithium ion batteries, so you will need to change it to that selection. Just hold down the gray button for several seconds, and it should start blinking for you. It'll let you cycle through each of the selections as you press down on the gray button. You'll want to set it to lithium ion, which is going to be a blue color, and you'll know it's set when it starts to blink blue on that charge controller. Note the order of the lugs on my setup. I put the solar charge controller on the top of the lug of the inverter, and the inverter lug is actually touching the battery directly. This is because the inverter will draw more power and should be touching the battery instead of the solar charge controller, which will not be putting that much energy into the batteries. Here's my battery's BMS reading as my solar panels are charging it in the remaining sunlight of the day in mid-December. Despite the fact that the sun is not at its peak power and is setting, and it's also December, we're still charging at about 18.6 amps, which is still a decent amount of energy. The maximum it would be able to generate under peak conditions is probably going to be around 22 amps anyway, so it's not terrible, but definitely not as good as it could be. As you can see here, we've lost power. We have no power in the community at all for about an hour now, and I'm probably going to start hooking up my battery system, close to my fridge of course, so I can preserve my freezer full of food here. Okay, as luck would have it, the power came on about 10 minutes after I shot the last part of this video, so obviously my fridge is now working on the regular AC power, but since I already set up everything, I wanted to make this video for a long time and just show how it works on the battery. So I have everything set up here. My fridge, as you can see, is connected to my inverter. Everything's off. You always want to plug it in when the inverter is off, so to make sure that it's flipped off and you do this. And just to show you, power's off. Let's go ahead and flip the switch here. It's going to be on this side. Here it is. Okay, got a beep. That's good. Everything's green. Don't hear much of the fan coming on to the inverter at this point. It's probably not much load at this point. So let's just see here. And look at that. The fridge is powered on. And as you can hear, it's blowing air, so it's doing its cool down thing. It only clicked on recently, so it's still trying to cool down after being off for about two or so hours. But as you can see here, you can actually power your entire fridge and freezer with just this little 200 amp hour, 2400 watt battery. So you could definitely last quite a bit of time on this. My calculations based on my fridge is probably about 3 solid days if I took it from basically about 100% to, well, pretty much zero. You probably want to avoid going to zero, but you know, if you had to, you know, if it was like an emergency situation, you could certainly bring it down to zero every so often. I would definitely encourage you to try to charge in between though if you can with your solar array, just to kind of keep it up a bit. But yeah, worst case scenario, you could run this basically about 3 days in this power, in this kind of a fridge here. If you have a bigger fridge, it may not last as long, of course. Obviously, the bigger it is, the more power it may draw. But yeah, so I'll show my battery stats right now to show you how much watt hours are being used by it. This is the draw with the fridge powered on, but the compressor isn't running at this point. The ambient draw is about 1.7 amps. With the fridge running after the compressor clicked on, you can see that's only presently drawing about 12.5 amps. The ambient draw is about 1.7 amps, so this means that the fridge itself is roughly pulling about 10.8 amps or about 130 watts from the battery. The power was not out for very long, so the fridge doesn't have to work much to keep it cool for now. If you want a more accurate assessment of how much the fridge will draw in a day, it's probably best to use a kilowatt device, since it'll probably be a lot more precise than the battery's BMS. It'll click on and off throughout the day, so it's not going to use 12 amps consecutively throughout the day, obviously. for hours and hours. It kind of clicks on maybe, I don't know, 15, 20 minutes, and then maybe clicks off for a couple hours and, goes back on and off. To store this safely for the next time, we're going to have to discharge the capacitors in the inverter. I'm going to disconnect the negative wire, so the black wire, and I'm going to hold it against the positive lead of the inverter, but I'm going to use the resistor here to do that. Obviously, you don't want to touch the wires directly because that would kind of defeat the purpose here. We want to control the discharge, not have it flow through and possibly cause some damage here. So okay, our system is now disconnected from the power, so the capacitor should be discharged at this point, and now we can go ahead and break this down if we have to. But for those of you who just have it connected all the time, you don't have to worry about this. Just kind of keep it connected, and that's basically it. Okay. Oops. See? Mistake number one, I did not check to make sure that my inverter was off, and it beeped. So it worked as it should have. Always make sure the inverter is off. That was my mistake. Okay, so now we're going to go ahead and touch the negative wire against the resistor, and we're going to hold against the positive end of the terminal on the inverter, like so. Just for a couple of seconds here. Make sure we get good connection. Okay, so this should be safe now. There shouldn't be a spark. Okay, so we safely discharged the inverter. So now we can go ahead and safely remove our battery out and move this. Now the overall cost of the system is going to vary greatly depending on what types of components that you buy. I wanted to stick with Renogy for my panels, charge controller, inverter, and battery, especially because they have a good reputation for quality and safety especially. The safety part is especially important to me with the battery because of the possible fire hazards associated with lithium-ion batteries in general. Now this is substantially diminished with lithium iron phosphate batteries, but even still I didn't want to chance it with something cheaper and that may not be made properly. It's possible and likely that the maker of Renogy's batteries could be selling under a no-name brand on Amazon or elsewhere for 30% or less, but that was not a risk I was willing to take. That being said, for the price I paid for this Renogy battery, about $950 at the time in April 2021, you could probably now get a 300 amp hour battery, possibly even a 400 amp hour battery on Amazon from a lesser known brand for about the same price. With all of my components, I probably spent close to $1,800 in the end for everything. This was with buying things strategically as they went on sale and leveraging 5% cashback rewards categories on my credit cards over a period of time since I was in no rush. Now, some of you may be saying for $1,800, you could have purchased a pre-made EcoFlow, Bluetti, or Jackery device and have it be professionally made and frankly, look a lot nicer and slicker than what this method allows you to do. This is a very valid point, but there are two issues with this. Number one is the fact that dollar for dollar, you'll almost always be able to have a higher wattage setup with a DIY route than you will with the pre-made route. This is due to the markup and premium that you pay for having a nicely made pre-made device like this. While it cost me about $1,800 to build this whole system, EcoFlow and others were selling 200 amp hour systems for closer to $2,500 or more at the time. Today, the EcoFlow Delta 2 Max portable power station is selling for around $1,750 and is still only a 2 kilowatt setup and doesn't include the solar panels, whereas mine is a 2.4 kilowatt setup and it's inclusive of the panels. The second issue with buying a pre-made system like an EcoFlow is the fact that if something goes wrong with it, such as the inverter, battery, or any other component, it's likely that you'll have to return it back to the company or an authorized repair shop for the repairs. I'm not really sure how DIY friendly something like that can be, if it's even possible, because not only would it most certainly void your warranty, but there's a possibility that they could also have custom-made components to fit their device's form factor, and acquiring these components on your own could be pretty difficult, if not impossible. We won't even get into the cost of the repairs to have it fixed by them if it's not a warranty. The fact that I built my system with off-the-shelf parts that are readily available makes me fully immune to this and allows me to customize each piece to my liking. If any of the manufacturers of the components that I used were to go out of business, I could simply just buy from another maker and just be done with it. If EcoFlow or the others were to go out of business, then you'd probably be out of luck. Now, by no means am I poo-pooing the manufacturers of these pre-made power station devices. They're beautifully made. I'm sure they will work terrifically for many years to come and only become more popular as prices go down. However, you're also dealing with someone here who has never bought a pre-made desktop computer in his life and has always built his own for the past 25 years. This is because of the high level of customization and interoperability that doing so affords you by putting in a little extra time to learn how things work on your own and how to build them on your own as well. You'll be learning a new set of skills that can prove to be useful to you down the road and maybe even set you on a new career path in the future with all the skills you acquired by doing this project or other projects in the future. If you're a little bit adventurous and are willing to learn, go the DIY route and learn how to do this on your own and build your own system to your liking. If you feel that this is not worth the hassle and want to spend your time doing other things that you enjoy instead, then go out and buy a pre-made system and be done with it. Either way, you're making a good choice to help you in a long-term grid-down scenario. If you can afford it, you may also want to buy a small gas generator to augment the system with, since solar and gas generators both have their short and long-term pros and cons to them. Check out my links below for all the components that I use to build my setup, but be sure to do your own due diligence to make sure all your power sizing and safety requirements are being met for your system's build.